Alright, so we're gonna start with some of the topics from earlier. So surface parameterization. And essentially the idea with this is it's very similar to like I think the regular parameterization from the single variable case, except we have two variables instead of just one. I think that's like basically the easiest way to describe it, and then just go straight into an example. Well, if I wanted to now for the intuition, like how to parameterize it, if I wanted to parameterize the surface x squared plus y squared is equal to z, for example, one thing I could do is just use the fact that x squared plus y squared normally gets easily parameterized with cosine and sine. And because I want two variables, I could do something like r of uv is equal to u cosine v, u sine v, and u squared, something like this, which essentially is supposed to satisfy the original equation that defines our surface. Yes, I can show you that this one will actually satisfy this one right here. U squared times cosine squared v plus sine squared v is equal to u squared equals u squared. Right? That's essentially the big, that is essentially just the big idea. To try to take something you know and apply it into something else.
Plug it in and then it's like it's equal and true or whatever. That's kind of how you check it.
Yeah, this is kind of how you would check it. If it asked you like if it gave you a parameterization and then said show that this parameterization satisfies this equation, then yes, this is how you would do it. You would essentially have like this first element is x, this second element is y, this third element is z. You would set those appropriately, and then you would plug these into the equation. Like so.
Wait, how did you get u squared equals u squared again?
Okay, so if you can see here, u cosine v squared, u sine v squared, we get u squared cosine squared v plus u squared sine squared v. I factored out the u squared and then got cosine squared v plus sine squared v. This is 1. So I have u squared equals u squared. And to reiterate, the cosine squared v plus sine squared v, that's just 1. And I think for like most of these, you just like borrow from like cylindrical or spherical. So like if I had like x squared plus y squared plus z squared is equal to 1, for example, which is actually just a sphere of radius 1, if you couldn't tell, then one way I could parameterize this is to borrow from spherical, but with rho is equal to 1, and then have everything else be phi and theta. So I could just have like sine u cosine v, sine u sine v, and then cosine of u, and this would parameterize the sphere. If you don't know where I got these, I essentially took these ones from spherical that I'm writing out right now. X equals to rho sine phi cosine theta. Sine phi, rho sine phi sine theta, and z is equal to rho cosine phi. And then I just set rho is equal to 1 because of the fact we have a 1 on the right side. And then I renamed phi to be u and theta to be v. So this is kind of an example of how you could do it for like a sphere. If you have an ellipsoid, then you would essentially just have to just change some of the parameterizations here, but it would mostly be the same idea. Any questions? One second. getting a lot of pings. Where is the pings coming from? Hang on, give me 1 second. Okay, nothing but okay. Oh, okay, it's just forgot to mute it. I forgot to mute it. That's why.
How do you mute the pings?
Oh, the pings. Let me just go. I think I'm going to just go to text channels, mute channel until I turn it back on. Okay, yep, it's muted. Yeah, make sure the other. Gonna just make sure the other ones are off. I don't know why it's doing this. Oh, yep, it should be mute calc 3 until I turn it back on. All right, now that that's out. All right, now that's out of the way. Let me see. So scalar and vector integrals and just mostly stuff like that. And so first, we're just gonna deal with the scalar. I'm gonna do the line integral. The surface integral is fairly similar, just a slightly different extra portion of this. So with a scalar line integral, you'd have something like c of FDS, where c is essentially some curve, and f is some scalar function. Some scalar function. Essentially, the idea is that for line integrals and similar case for surface integrals, is you parameterize the curve, c in this case. You rewrite f in terms of the parameterization. And finally, you rewrite ds, which is essentially the same ds from arc length. So this is the magnitude of the derivative of the parameterization with respect to the parameter, and then dt, which is the delta t, that tiny bit of t, and this is essentially just a function that tells us roughly the arc length. So this is the case for a scalar line integral. When we have it like this, for a vector line integral, we have something like capital F dr. The same two steps as before. Only this time our dr is going to be equal to just r prime of t dt, like so. And then again we parameterize f of rt. We parameterize f of rt, and then we're dotting the two instead of taking the magnitude of the vector function of this vector function here, or really the magnitude of the derivative of the vector function. All right, so that's good. It for that. Just a slight review of line integrals. For surface integrals, it's a very similar story, except we're going to have like a double integral of some surface S. So we're going to start with the f ds like this. Here's d capital S. This is similar to line integrals in the sense you're going to again parameterize the surface, except here in this case your ds, instead of just going to be the magnitude of the derivative here, because we're going to work with multiple different variables at the same time for the parameterization, we'll have something like this, where we have magnitude of the partial with respect to u cross the partial of r with respect to v, like so. And for a very similar thing for the vector, like this, I'm gonna put a tilde for this s because it's a slightly different one. So this ds tilde is just going to be just the vector ru cross rv, and you're going to dot f, which is a vector function, with the whatever vector you get out from the ds. All right, and that's mostly the gist of what you're doing for line and surface integrals when evaluating these. Any questions?
So these are three different concepts that are slightly different.
I mean, they are the idea is that these are like the scalar and vector line integrals are similar to each other, and the same for the surface integrals, and they're all like similar in how you're evaluating them. In the sense, you always parameterize the curve, you always rewrite the function you have in terms of the parameterization, and then you're calculating a very specific ds or dr, which is like given, which changes depending on like which integral you're doing. If it's a vector one, you just have the vector function itself. If you have the scalar one, you use the magnitude. Yes?
Do you think you could talk a little bit about Green's theorem and like the fundamental theorem of line integrals after that?
Sure. Okay, so first I'm just going to start with Green's theorem. So, Green's theorem is going to be for when C, which is the curve, is a simple closed curve. Simple here meaning does not cross itself. Does not cross itself. Closed does not have. I'm actually going to use a different. Closed means it's enclosing a region. Encloses a region, basically. This is best just given by like a small example. Well, an example here is this circle that I just drew here, which will have radius of 1. This is a closed curve, because as you can see, the circle here is completely enclosed by this curve. So that's what I mean by closed. And essentially what Green's theorem is saying is that this integral of FD of the integral across the curve of f dot dr is going to be the double integral over the 2D region that it encloses. This is D. The 2D region enclosed by C of q of x minus py dA. Now, what do I mean by qx and py? Well, our vector function is going to be some function p of xy, q of xy, like so. And essentially what this is saying is partial derivative of q with respect to x minus the partial derivative of p with respect to y. And then if the field is conservative, if f is conservative, we already know this is going to be 0, but it's going to show, but this one shows it fairly cleanly y. Q of x is equal to p of y. So qx minus py is equal to 0, which makes it independent of the region. And it's just 0 no matter what. And the idea with Green's theorem is you can go from one to the other, whichever one is easier to work with. So in one of the examples from the lectures, you had to go from this version with the double integral, because you were trying to find an area, so you wanted a double integral of 1 dA, and you wanted to go to the line integral version of that, because you tried to solve this one, but we were not sure how to make the region work, at least in the double integral. But the single integral, we could make that work, because the curve was easily defined. And by easily defined, I mean the definition of the curve was literally given to you, or the equation or whatever. And that's the big idea for Green's theorem. You have this equality between these two whenever C is simple and closed, and it closes region D.
So could you do one problem example?
Sure. Sure. I think I'll do the one from the lecture notes. So this is the one with the x squared plus y to the 2/3 is equal to 1. That was from the lecture notes. And then this said to find the area of the region enclosed by C, which is given to be this function here. This is in your lecture notes, but I'm going to go through this one again because I like how this one goes, really. I'm just going to stop once we get to the evaluation point, because that part is going to be just tedious, and I think it's not helpful. So essentially the idea here is C is including some region D. We don't know how to define this region D, but an area is going to be given by 1 dA. From Green's theorem, we can see that this is closest to this double integral version. So I want q of x minus p of y dA. And then we want to find a vector field such that q of x minus py is equal to 1. Really, any vector field will do for this one. I think for the sake of ease, we're just going to do, let's see, 0x. For this one, we'll just define this to be f. And now we're going to convert this into a line integral using Green's theorem. We're now going to have the single integral over C of 0, x times, or dotted with, dr. Now, we need to parameterize this somehow, so we actually have a dr to work with. So here we need to essentially parameterize x squared plus y to the 2/3 is equal to 1. So the idea with parameterizations like this is to try to find the closest thing to it that you do know the parameterization of, and can just convert from one to the other. So in this case, I can see that this one looks incredibly close to x squared plus y squared is equal to 1, except instead of y being squared, it's y to the 2/3. And I know this one on the right here, x squared plus y squared equals to 1, is parameterized with r of t is equal to cosine of t sine of t. So for our new curve, we're still going to have the cosine of t, but because we essentially have a cube root applied to the y squared, I'm going to use sine cubed to make up for that. So this r of t here, cosine t sine t, is going to be our parameterization. Also from from 0 to 2 pi, basically t is between 0 and 2 pi. So we have integral of t is equal to 0 to 2 pi of, and then we're going to use the fact that we have a sine cubed t here. So x is equal to sine cubed, or cosine t, my god. X is equal to cosine t on this one. Cosine of t dotted with the derivative of our r of t. So now we just got to find the derivative of this. negative sine t sine cubed t. Not sine cubed. 3 sine squared cosine. 3 sine squared of t times the derivative of the inside, which is cosine of t. So negative sine t.
Can you explain how you got the cubed?
Okay, so do you see on the right side, x squared plus y squared equals to 1? And we know that parameterization to be cosine t sine t, correct?
Yeah.
Okay, so here on the left, which is the original one, we almost have this one, except instead of y squared, we have y to the 2/3. So we essentially want to cancel out the extra 1/3 here. So I'm going to cube the y part of the parameterization in order to make this essentially a sine squared again. So here is like y squared to the y third is equal to sine squared t. So y squared is equal to sine to the 6th t, and therefore y is equal to sine cubed t.
Okay, thank you.
No problem. And then the rest of this is just dotted with this, dt. And then t is equal to 0 to 2 pi of, the 0 here will cancel stuff out, so we're just going to get 3 sine squared t cosine squared t dt. I'm going to stop here as far as the problem, because this is just evaluating the integral, and don't want to do it. So, yep, that's Green's theorem taken care of. I think fundamental theorem of line integrals was wanted. So I'm just going to go ahead and go through that one. I think this is a fairly quick one.
Thanks. Yeah, and specifically it says we need to like see how the fundamental line theorem like relates to Green's theorem or whatever.
Okay, so I think relates to Green's theorem. I think you get like I think the part that will relate to this one is like the mixed partial thing. Because if f is conservative, because the only time when the fundamental theorem of line integrals applies is when you have a potential, is when your vector function f, capital F is always going to be a vector function, by the way, is equal to the gradient of some potential scalar function, little f. So I have f is equal to gradient of f. This is the only time where fundamental theorem of line integrals will apply. The way this will be true is if f is conservative. If capital F is conservative. So Green's theorem would say that this would essentially say that for any simple closed curve, it's 0. This whole thing becomes a 0. Says if C is a closed curve, then the integral of C of f dr is equal to 0. That's basically what Green's theorem is saying here. Mostly because Q of x has to be equal to P of y, which we said makes this whole thing, makes it 0. That's really about how, I think, how fundamental theorem of line integrals will relate to Green's theorem in any way. It will just tell you if C is a closed curve, this whole line integral becomes 0. And then the actual fundamental, no problem. And then the actual fundamental theorem of line integrals is saying that this one with the gradient of f, with little f dr, is just f of r of the starting point, which I'm just going to say. I'm just going to do t equals to a to b. F of r of b minus f of r of a. Like so, that's the actual That's the actual fundamental theorem of line integrals. All right, is there any other topics that I should go over, or should we just go straight into the exam review problems? Anyone?
What was the difference between the small f and the large f?
Okay, so the small f is essentially a scalar function. The big F is going to be a vector function. I should probably use an arrow for denoting a vector function. Okay. Let me just see if there's any last questions, and then we're just gonna go straight to the exam. Well, what's happened so far? Just review of some topics on line integrals and Green's theorem for the most part. All right. If there's no further questions, I'm just gonna go straight into the exam review problems. All right. I'm just gonna use a new section of the board. Exam review problems. Number 1 asks to answer the following true-false questions. If it is true, explain why. If it is false, give a counterexample. I'm just going to write true/false. A says it is impossible for a vector field to be incompressible. Well, this means div f is equal to 0 for some vector function f, and irrotational. So this means curl f is equal to the 0 vector. All right, anyone want to give any guesses for what this is? What? True?
No, not true.
Not true?
Can you explain what's asking?
Okay, so this is a true/false question, and 1A is currently saying it is impossible for a vector field to be incompressible and irrotational. Is this true or false, and why? Oh, okay.
What does it mean to be incompressible and irrotational?
Incompressible means if you take the divergence of f, you'll get 0 for I think anything, and then for irrotational, curl f is equal to 0.
I think this is true because I think with dive, you're doing the dot product, while with curve, you're doing the cross product.
All right.
And I don't think both can equal 0.
Okay. So we got 1 true and 1 false for now. Anyone else want to give a guess?
Actually, I changed mine to true.
Okay. Yeah, I think I was going to go false with this one, actually. And for the main reason, like, suppose we had a vector field of all zeros. So if I do of all zeros, which means essentially it is nothing is moving. This is still a vector field that we have defined. It just means at any point it doesn't move. Nothing moves. The divergence would be 0 because partial with respect to x of 0 is 0, 0, and another 0. And if I computed the curl of f, I, j, k, partial x, partial y, partial z, 0, 0, 0. So we have 0 minus 0, 0i minus 0j, 0 minus 0, plus 0k, which is equal to the 0 vector. So we have found a vector field that is incompressible and irrotational.
So for the divergence one, you're just taking the partial derivative of x, y, and z.
It's essentially this differential operator dotted with the vector function. And this differentiable operator is like partial with respect to x on the first, partial with respect to y on the second, and partial with respect to z on the third.
Okay. Yeah, thank you.
Yep, dotted with 0, 0, 0 will just give us 0. So therefore it's false. And this is and our counterexample is 0, 0, 0. All right. Does everyone see where I got that from?
Yeah.
All right, I'm moving on to B then. B. This one's I think a little bit more of a complicated one. If div f is bigger than 0 for f in R2, then Fn is bigger than 0 everywhere where, let me make this a little bit smaller. N is the normal vector to a unique, not unique, unit circle oriented outward. In other words, f dot n bigger than 0 means that everywhere on the unit circle, the vector field points outwards. My god, this is a long question. All right, anyone want to give a guess on if this is true or false? Anyone?
What does divergence of f mean?
So divergence of f is like a tendency for a certain fluid or whatever to go away from a specific point. So outward from a point, basically.
Can you show that visually?
Yeah, sure. So here is like if div f is bigger than 0, we'd have something like this all around the vector field, where essentially more is flowing out than is flowing in. Here, nothing is actually flowing in, everything's flowing out.
So it can't be a rotational vector field?
This is not talking about irrotational here. That's a curl thing. This is a divergence thing.
Okay.
All right, div f is, and also here's a few other examples. If div f is less than 0, you're going to get more flowing in than out. So you're going to get something that looks like this diagram. And then div f is equal to 0 means you're going to get some flowing in, some flowing out. Something like this. Basically, an equal amount flowing in that is flowing out. So something like this, I think, would be a good example of div f equals 0. All right, with that in mind, does anyone want to give a guess?
I think it's true.
Yeah, I also thought it was true as well. For the main reason.
If it's greater than.
Yeah?
If it's greater than 0, does everything have to be pointing outward, or can like some of them be pointing inward?
Some can be pointing inwards. The idea is that more is going out than is going in. This is purely just to illustrate the point.
So, could they answer this
But
question?
on the question it says that everywhere is pointing up.
Yeah, it says everywhere, but in other cases it doesn't all go outward. You said some can flow in.
Some can, but look at the first portion of this. Look at the first portion of this. Before it says that. before it says it everywhere. There's one portion of this that I think will solidify true here.
F dot n.
Not the f dot n, before that. Look at the condition.
Contained in all of R squared.
It says if div f is bigger than 0 for f in R2. So it's going everywhere. So it is actually everywhere in this case. So since div f is bigger than 0 for f in R2, everywhere a fluid would flow away from a point or outwards from a point more than inwards. Thus, this is also true for the unit circle. Since n points outward, f dot n is bigger than 0 everywhere. All right, everyone got that? Or do I need to explain anything?
What does the f dot n greater than 0 represent?
So in the last sentence here, it says everywhere along on the unit circle, the vector field points outward. It's just straight.
Like 90 degrees, basically, like perpendicular directions.
I think n is the n is the normal vector perpendicular to a unit circle. And since this points outwards, and we know everywhere it points outwards, which will also be true for anything along the unit circle, Fn must also be pointing outward, or bigger than 0.
Wait, why doesn't f equal 0 fit into that category?
F equal to...
It's not...
Okay, you got it? Yeah, because div f is bigger than 0 here. All right, I'm going to move on to C. Consider the vector field f is equal to negative y over 3, 2x over 3. Okay. I'm going to have to write this slightly differently because they write it weird. The integral C on C f dr gives the area of D enclosed by the simple closed curve C. All right, anyone want to give a guess? Anyone? I think we did something similar to it. Yeah, I would also go with true as well. And here's the reason. So, you all remember? Do you all remember Green's theorem? We just went over this one, but I'm going to say it anyway. So this one was C f dr. I'm going to put this circle thing here because this just means that C is a simple closed curve, which is indeed the case here. Here, actually, that should be the case on here too. Green's theorem. Where is it? Yep, I'm going to put it there. That should be simple closed curve. Q of x minus P of y dA. Now what's q of x minus p of y? So the partial of q with respect to x. So this is q. I'm going to put p q. Q, we have 2/3, because it's 2/3 x, minus negative y over 3 will give me negative 1/3. This is equal to 2/3 plus 1/3, which is equal to 1. So this is just the integral of dA. And this is the area of D. True. And that's it for 1. Any questions, or do we move on to 2? All right. I'm just going to go ahead and move on. Compute the following integrals. Okay, let's start with A. Squared plus y squared dy dx. All right, so first we're going to take the integral of this with respect to y. So we have x squared y plus y cubed over 3, evaluated from y is equal to 0 to 2. So at y is equal to 2, we're going to get 2x squared plus 8 over 3. And then at 0, this portion is 0, and this portion is, and the y cubed of 3 will also yield 0, so I can just stop there. And then the integral of this is going to be 2/3 x cubed plus 8/3 x, evaluated from 0 to 2. At 0, I'm noticing I get 0, so I can just plug this in for 2. 2 cubed plus 8/3 times 2. This is equal to 16 over 3 plus another 16 over 3, or 32 over 3 for our answer. B is actually the same problem from 11B from the previous exam review. So do you want to skip this one, or should we do it again? Because it's literally the exact same problem that we already did on the last time.
I think we just do everything off the game. Scroll up, please.
Sure. Okay, we're gonna do it. We're gonna do it then.
I thought no, wait. For y, it's from 3 to 0, not from 2 to 0.
Oh, I messed it up here. Yep, that should be a 3. You're right. Give me 1 second to fix this. This should be this, and then 27. This is just gonna be 9. 9. That's why. So this is just x cubed plus 9x. And I think you get 26 from this instead. Okay. 26. Yep. 8 plus 18. 26. All right. I'm gonna just do. We're just gonna do B again. And I mean, it's literally 11B from the previous one. So yeah. But let's just do it anyway. So first, I'm just gonna do that. I think x cubed is a cubed. I think it's like, oh yeah, it's below x squared for this one. So something like this. This is the region in question. Actually, the intersection points are just going to be 0 to 1. 1. Here's a fairly simple demonstration for this. Or actually, I'll just do it the other way. So x equals to 0 to 1, and then y, here's cubed to x squared, y minus x, dy dx. And this is the type 1 version. And for the type 2 version, you can see here that y will also go from 0 to 1. And then we essentially have to calculate x. So the x cubed term is going to be to the left. Yeah, actually x cubed is to the right. X cubed is to the right. So we're going to have x is equal to square root of y. And then I think we're just going to get x is equal to cube root of y on the top.
Are you just rewriting the equation?
Yeah, we're essentially just rewriting like y is equal to x squared and y is equal to x cubed. X is equal to root y. X is equal to cube root of y. We only want the positive anyway because this entire thing is confined in the first quadrant.
Type 1 is x first or y first?
Type 1, I think is going to be the x first, and then type 2 is the y first. So we have the type 2 version here. This is way easier. And then the type 1 version, which I am just going to plug in a point for this. This, I think, easiest one to plug in is going to be like 1 over like the first 6/3, that isn't that, so 64. 64, this is going to give you 1/8, and then this. And to give you 1/4, yep. Yep, this is indeed the right one. Y minus x dx dy. We're going to evaluate the type 2 version of this because I'm lazy and I like the easy one. I like this easy one. Y squared over 2 minus xy, x cubed to x squared, and then we get y is equal to x squared. We're going to get x to the 4 over 2 minus x cubed minus x to the 6th, and then we have x to the 6th over 2 minus x to the 4th. X is equal to 0 to 1 minus x cubed minus x to the 6th over 2. We have plus an x to the 4th plus another x to the 4th over 2, so I'm going to have 3 halves x to the 4th. And this should be negative x to the 7 over 14 minus the 4th degree term is actually a plus 3x to the 5th over 10 minus the x cubed term is x to the 4th over 4. Evaluated from 0 to 1. 3/10 minus a 4th minus a 14th. And that's the answer. So let me see if I do any. No, this should be good. All right. 2C. Integral from 0 to 1. Integral from 0 to 1. E to the x plus y dx dy. This is just e to the x plus y, 0 to 1. So x equals to 0, we'll just get e to the y. And then x equals to 1, we'll give it e to the 1 plus y. This is going to be e to the 1 plus y minus e to the y, evaluated from y is equal to 0 to 1. So we get e squared minus e minus e minus 1. Or e squared minus 2e plus 1. Also known as e minus 1 squared. Awesome, let's move on. Let's move on. D. Integrate xy over the portion of the unit circle above y equals absolute value of x using both Cartesian and polar coordinates. So we're going to start with the region. Let's see if I can. What? So the portion of the unit circle. So I'm just going to mark off 1, 1. And there should be a negative 1. 1 and then a 1 here. So we're going to have something like this. And then absolute value of x is going to just do something like this. Like so. Now in Cartesian, we are going to have. I think I think you might have to set this up as two separate integrals, or use the absolute value of x, or just use y is equal to the absolute value of x, and y is equal to the square root of 1 minus x squared, which comes from the unit circle itself. Y squared is equal to 1 minus x squared. And then we can ignore the negative because this entire thing is confined in the first and second quadrants where y is positive. And then we'd essentially just find where the intersection point is between the two. I think this is put, which I think, if I remember correctly, should be root 2 over 2, negative root 2 over 2 to root 2 over 2 for this. It's the easiest way to do this is to just set them equal to each other because of the absolute value. I'm going to just destroy it into x and negative x. Next, oh wait, they get the same, oh wait, you get the same thing either way, so it's just going to be this. 2x squared is equal to 1, x squared is equal to 1 half, x equals plus or minus root 2 over 2. So this would be that, and then it says integrate x, y. dy dx. And you're gonna have to split. Yep, you're gonna have to split that one in order to do this. In polar coordinates, you get. Yeah.
Where did you get the x equals square root 1 minus x squared from?
Oh, that comes straight from the unit circle.
But you have x twice.
Huh? What do you mean x twice?
Because if you're referring to the unit circle where it's y squared plus x squared equals 1,
yes.
Where is the y in that equation?
X squared plus y squared equals to 1. It's in there. There's a y in the equation. We're gonna isolate for y, which gives you plus or minus. But then because it's entirely confined into y bigger than 0, we can get rid of the negative.
And the x equals square root 1 minus x squared.
X is equal to square root 1 minus x squared, yeah?
You got that from the unit circle equation?
Oh, that one is from both the units. The right-hand side is from the unit circle. The left-hand side is from the absolute value function.
Can you explain that in more detail?
Okay, so in the problem, it says it's bounded by absolute value of x, which is these two straight lines, and then the unit circle, which is this which is the curved line. We want to find the intersection points so that we can find what x is bounded by, at least concerning this region here that I'm about to shade. So the idea here is we have absolute value of x is equal to the square root of 1 minus x squared. So to do this, we're going to square both sides. We're going to get x squared is equal to 1 minus x squared, and then solve that for x.
So because they're both equal to y, you can equal them to each other and do that.
We're trying to find the intersection where the two lines or two graphs intersect. So that's why we're going to set them equal. So we're going to set them equal to each other from that way. And yes, because they're equal to y, both equal to y, we'll set them equal to each other to find where they meet.
Okay, thank you.
No problem. All right, that's the actual integral. I think I'll just set it up in polar and just evaluate that one. Now, y is equal to x and y is equal to negative x are fairly simple here. You'll get r cosine theta is equal to r sine theta. For the first one, which just becomes cosine theta is equal to sine theta. So therefore, theta is equal to pi over 4. And then for the other one, you get negative cosine theta is equal to sine theta. And this occurs at theta is equal to 3 pi over 4, between 0 and pi. So theta goes from pi over 4 to 3 pi over 4, with r going from 0 to 1 because of the unit circle. And finally, we have xy to deal with, which is going to be we have r cosine theta times r sine theta, r dr d theta. Theta is equal to pi over 4 to 3 pi over 4. R is equal to 0 to 1 of r cubed sine theta cos theta, dr d theta. And now we're going to solve this one. R to the 4 over 4 0 to 1, and then sine theta cos theta. I'll leave that one alone. Theta is equal to pi over 4 to 3 pi over 4. And then we get 1/4 sine theta cosine theta. And I think I'll just take the route of using the fact that sine theta equals sine of 2 theta is equal to 2 cosine theta sine theta, or 2 sine theta cosine theta, to say that this is just 1/8 sine of 2 theta. Because there's two routes you could use for this integral. Sine of 2 theta will give me negative 1/2 cosine of 2 theta. Evaluated from pi over 4 to 3 pi over 4. Which is equal to negative 1/2 times cosine of 3 pi over 2. Oh, that's going to be nice. And that's 0. Because this portion is equal to 0 and this portion is equal to 0. So it all cancels out. Heck, even the 1/8 didn't matter. Okay, moving on.
Can you explain the conversion from Cartesian to polar again?
Okay, so the conversion is essentially, we have three different equations. X is equal to r cosine theta, y is equal to r sine theta. And that's basically it. The other one's like z equals to z, but that's not important here. So this is x equals to r. This is essentially the conversion equations for polar. And essentially, that's what we use to calculate all these intersection points and the bounds. Oh, and also x squared plus y squared equals r squared. And also that one. For the unit circle, we get x squared, we get that r squared equals to 1, so r is equal to 1. 0 is less than or equal to r is less than or equal to 1.
How did you get your thetas?
The thetas, we just took the absolute value of x, broke it up into two separate lines. One of them gives you cosine theta equals to sine theta, the other one gives you negative cosine theta equals to sine theta. The cosine theta equals to sine theta one should be fairly easily recognizable as theta equals to pi over 4. You can use the unit circle to find out why. And then the other one is cosine theta equals to negative sine theta, which will be 3 pi over 4. Because at 3 pi over 4, cosine is negative if sine is positive, and the absolute value of cosine theta and sine theta are equal at pi over 4. At pi over 4, 3 pi over 4, and 3 pi over 4. So these are going to be the bounds. Any other questions?
Where did you get the y equals minus x minus cosine theta?
Yeah, okay, so this should be an implied, but the y equals to negative x is coming from the absolute value. It's coming from the absolute value. Notice that at the positive portion, we have y is equal to x. On the negative side, on the side where x is negative, we have y equals negative x. This follows from the definition of absolute value. This thing. So that's where we get our two equations. Any other questions? All right, moving on. E. This one actually I don't so makes that much sense, but I'm going to do it when I just compute it. So we have r squared over 2 evaluated from, yes, I have no idea why I did this. It's from negative r squared to 1 minus r squared. So we get 1 minus r squared over 2 minus negative r squared over 2 d theta. I'm just going to simplify this out. This should be r to the 4th minus 2r squared plus 1 plus another r squared. For 1, we get r to the 4th minus r squared plus 1 over 2 d theta. This is just r to the 4th minus r squared plus 1 over 2, all times theta evaluated from 0 to 1, or r to the 4th minus r squared plus 1 over 2. And that's the answer. Any questions? Because this is the reason why we don't actually get a value here is because this is a badly set up integral. Nothing at all. Okay, move. Okay. 2f. Huh? Yeah? You can speak up if you want to. I encourage it. Oh, let me see the chat. Yeah, see the chat.
If the integral was d theta then dr, would it result in a value?
Yeah, it would probably result in a value. Yeah, we can do that one. Okay, let me just see. Okay, someone asked for the other one. Is the final answer 0? For 2D, yes. For 2D, yes, the answer was 0. So it was 0, and yeah, you can also use sub on that one. There's two different ways. Yes, I said earlier that there were two different ways. Okay. Anyways, so if I did r d theta dr like this, here is the result that'll happen. negative r squared to 1 minus r squared dr. This, you can see, will result in an actual value. Zero to 1 of r times 1 minus 2r squared. I don't know, it should be plus. This should be a plus. Plus, so you just get 1. So you just get rdr, which just becomes r squared over 2 evaluated from 0 to 1, which becomes 1/2. So yes, you get an actual value for this if they were swapped. Any other questions? All right, I'm moving on. dz, dy, dx. Okay. Z squared over 2 evaluated from 1 to 2 sine of y dy dx. I'm just going to calculate this off to the side. 2 squared over 2. 2 is just 2, and this is just 1/2, so we're going to get 3 over 2. Three over 2, 0 to 1. And the y is going to become x times negative cosine of y, evaluated from 0 to pi. Negative cosine of y. Damn it. Okay, we're back. Evaluated from 0 to pi. Equal to cosine of pi is -1, so we're going to -1, so negative of -1 is 1. Minus -1, this is just equal to 2. So this is going to become 3 times the integral from 0 to 1 of x dx. X squared over 2 evaluated from 0 to 1, this is going to be 3 over 2. That's it. All right, on to G. Integrate z over d, where d is in the first octant. D in first octant. Below, z is equal to x square root of x squared plus y squared, so this is the top bound. And is inside x squared plus y squared plus z squared is equal to 9. Okay. So, the first thing we're going to do is just draw what this looks like. X, y, z. So z is equal to square root of x squared plus y squared is just going to be a cone. It's just going to go out something like this. And then somewhere along that, probably around here-ish, we're going to have some sort of sphere. Something like that. something like this, and then it's something like this bottom region here, below the, something around that bottom region. So first below the cone, the easiest thing you can do here is just to make everything into spherical coordinates because we have a sphere and a cone. So the first one, x squared plus y squared plus z squared equals to 9, will become rho squared is equal to 9, which means rho is equal to 3. Z is equal to square root of x squared plus y squared. It is going to become phi is equal to pi over 4, or you could just do rho cosine phi is equal to rho sine phi, which becomes cosine phi is equal to sine phi, which means phi is pi over 4. So those are the bounds for rho and phi. Now, because this is in the first octant, theta is only going to go from 0 to pi over 2. First octant. Okay. So now we're going to set this up. So rho goes from 0 to 3. Now, for the phi bounds, while phi is equal to pi over 4, it defines the cone. We're actually going below the cone. So it's actually this portion here. I don't think so you could, so you can see it. I'm just going to put it in blue. This portion here is going to be for the actual phi bounds. So phi is equal to pi over 4 will be the lower bound, and then the upper bound will be given by pi over 2 since we're in the first octant. And theta is equal to 0 to pi over 2. And finally, we have z, which is just rho cosine phi. Rho squared sine phi d rho d phi d theta. Rho cubed, and then I'll make it sine phi cosine phi. This is equal to, and then get rid of the first integral. We're going to have rho to the 4th over 4th. We'll evaluate it from 0 to 3. Which is going to be 81 over 4 minus nothing. Zero to pi over 2. I'm going to put 81 over 4 times, now sine phi cosine phi will become 1 half. Oh wait, that's going to be the sine of 1 half sine of 2 phi, which is going to become negative 1/4 cosine of 2 phi at the end. This is equal to negative 1/4 times now at pi over 4 we'll actually get cosine of pi over 2, which is 0. Well, so we're going to get negative 1. And then cosine of pi is negative 1. 1. So we're going to get that this is actually another 1/4. So this is 81 over 16, 0 to pi over 2 of d theta, or 81 pi over 32. Alright, that should be it.
Can you explain the process of converting z to phi?
Converting z to what? Z to phi?
Yeah.
Okay, so z is equal to rho cosine phi. And then the way we got the phi bounds here was we used the fact that it was in the first octant. So z was bigger than or equal to 0. And anything from phi equals pi over 2 to pi has z less than 0, so it's off limits. And then the cone was given by phi equals pi over 4. So that's going to be the other bound. So we have phi between pi over 4 and pi over 2. And then z equals rho cosine phi was one of the conversion equations for spherical. Any other questions? Alright, I'm moving on. Number 3. This asks us to consider an integral, or actually multiple integrals, of f of xy dy dx, plus the integral from 0 to 1, and the integral from negative square root of 1 minus x squared to square root of 1 minus x squared, f of xy dy dx. A asks us to sketch the region, so we're going to sketch this. X and y. So to start off, let's do the one on the right first. Why? Because this is just going to be a circle. No, just the right half of a circle of radius 1. Why is that? Because we have y equals to plus or minus 1 minus x squared, square root of 1 minus x squared, which is y squared equals to 1 minus x squared, or x squared plus y squared equals to 1. And because of this, we have a unit circle, but because x is confined between 0 and 1, we're only going to have the right side. And for the one on the left, we have it confined by x is equal to by y equals negative 1, and then x plus 1, which will have an intercept at 0, 1, and it's going to do something like this. This is negative 2, by the way. So this is the region right here, this weird looking thing. So for B asks us to consolidate these integrals, these two integrals, into a single integral. So the way we're going to do that is we're going to actually use the y is equal to x plus 1 here, and then this is just y is equal to actually, you're going to have to do this with x for. Actually, you're going to have to do this with x is equal to square root of 1 minus y squared. Or this y equals to x plus 1 will also have to be converted, so we're going to get x is equal to y minus 1. And we're going to start with the x first, which means we go from the left side to the right. So x is equal to y minus 1 first, to square root of 1 minus y squared, and y clearly goes from negative 1 to 1. F of xy dx dy. And that's all of 3. Doesn't ask us to evaluate this. Number 4. Reverse the order of integration for the integral from -1 to 2 of the integral from x squared to x plus 2 of f of xy dy dx. So first we're going to just sketch this. So first we have y equals to x squared and also x plus 2. So y equals x squared, we'll do something like this. And a similar thing on the negative side. And then x goes from -1 all the way up to 2. We're just all the way out here. And finally, we also have x plus 2, which is going to be going from 0 to 2 all the way up to this line. This is not to scale at all, but whatever. Now, this should intersect actually between like this. And this is the region. And what it's asking us to do is to reorder this, so we need to have the x first. This means we're going to have two separate integrals. One between the 0 and the 1. One where it's going from one side of the parabola to the other side of the parabola. And one from 1 to wherever this intersects. This will intersect actually about at 4. Because x 2 plus 2 equals 4. And that's all we're going to have to do. So this becomes integral. So starting from y equals to 0 to 1, we're going to have x go from negative the square root of y to the square root of y. dx dy. We're going to have a second integral from y is equal to 1 to 4, which means it goes from this line that was defined by y equals to x plus 2, which means x is equal to y minus 2. This 2 all the way up to the square root of y. And this is the reversed order. Any questions? Hello, whoever just joined. Okay, I am going to move on then. Number 5. Consider the region R within the sphere of radius 2 centered at the origin and outside the cylinder of radius. It actually writes of radius twice here, but I'm only writing it once. Centered on the z-axis. A says to describe R in spherical, oh god, cylindrical and Cartesian So first R in Cartesian. Or actually, let's do cylindrical first, because that's the easiest one. So the cylinder of radius 1 means that the cylinder is essentially going to be described by r is equal to 1, and the sphere of radius 2 is going to be described by r squared plus z squared is equal to 4. So this means that z squared is going to be equal to 4 minus r squared, or z is equal to plus or minus the square root of 4 minus r squared. So r is going to be equal to, I'm going to use set notation for all the regions, because it's easier this way. The points x, y, z, or actually I'm going to use r theta z, such that we have the following: negative root 4 minus r squared is less than or equal to z is less than or equal to the square root 4 minus r squared. R goes from 1 to 2. The 1 is coming from the cylinder that's getting emitted, and the 2 is coming from the sphere. And theta goes from 0 to 2 pi, because there's no restrictions on it. It can be anything. So that's R in cylindrical. In spherical, I am just going to do, we have rho squared is equal to 4. Rho is equal to 2. This, I think, was going to suck to do, because the cylinder is going to be the worst of it. So we're going to just draw whatever the cylinder is. I'm just going to draw this region. X, Y, and Z. Yeah, we're going to have essentially this is not a two-scale drawing, but it will work for now. Something like this, where this is chord out. Essentially have a cylinder radius 1 chord out. What do we actually do for this one? It's 1. We know rho is equal to 2, and then theta will still be from 0 to 2 pi. Right, I need to find where this intersects at. Or use the fact that r is equal to, or use the fact that 1 from rho sine phi is less than or equal to 2. Just give me 1 second, just need to figure this out. Which means we have 1 over rho is between sine phi and less, which is less than or equal to 2 over rho. Oh wait, that doesn't work if rho is 0. Oh wait, rho can't be 0. Rho can't be 0 because that's that. Over there. There we're gonna have the cylinder is also defined by rho is equal to 2 cosecant phi, so that could just be the bottom bound. I think, yeah, that actually might be it. The cylinder, and then everything out from that up to 2. So yeah, okay, there we go. There's the logic. So the cylinder is going to be defined as rho is equal to 2 cosecant phi, from the fact that we have rho sine phi is equal to 2. 2 actually, root 2? No, it's 2. Because it's the radius. Yes, or is it? Oh my god, why am I messing up? Why am I messing up here? Cylinder defines it as rho sine phi is equal to 1. Cosecant phi to 2. And then phi can just go from 0 to pi. And theta is just 0 to pi over 2. Oh wait, this is not this. Oh, this is describing R. That's setting up the integral. Okay, so rho theta phi such that rho is equal to cosecant phi is less than or equal. This is less than or equal to rho is less than or equal to 2. The cosecant phi is coming from the cylinder because of the fact that mostly because of the fact that we have R is in the cylinder was originally defined as R is equal to 1 and R is equal to rho sine phi, so we're going to have rho sine phi equals to 1. So therefore rho is equal to cosecant phi. So we have cosecant phi is less than or equal to rho, which is less than or equal to 2. For phi, we're going to have between 0 and pi, because it stretches over the whole thing, minus that entire portion, but I don't think so it'll matter. Matter? Oh yeah, it does. Oh yeah, it does matter. Darn it, I have to actually find that value. The value of phi. There's one on this side and then one on the other side. Which is just this and then pi minus that. So the top here is going to be at a radius of 2. At a radius of 2, and the cylinder has a radius of 1. And so phi 1 is going to be the tangent inverse of 1/2. Oh, I don't think so there was an easy one for this one. We go from tangent inverse of 1/2 to 1/2 minus this. To pi minus this. Because it's also there on the other side. And 0 is less than or equal to theta is less than or equal to pi. To 2 pi. Because there's no restriction. Alright, that's it. That should be it for spherical. Well, Cartesian. I might just do this as a sphere minus a cylinder. Yeah, I'm just going to do this as I'm just going to do this as a sphere minus a cylinder. So x, y, z, the sphere is defined as x squared plus y squared plus z squared is at most 9. Not at most 9, 4. And then backslash the portion, the set of all points x, y, z, such that x squared plus y squared is less than or equal to 1. I'm just going to use set notation for this region. B asks us to rewrite an integral in Cartesian coordinates. It asks us to rewrite this b d rho d theta d phi into Cartesian. Okay, this is going to be I think two separate integrals. I think just two separate integrals. The first one is going to be in z. We're going to have x squared plus y squared equals to z plus z squared is equal to 4 becomes is z squared is equal to 4 minus x squared minus y squared, or z is plus or minus root 4 minus x squared minus y squared. Squared, so that's going to be the first one. Z is equal to negative root 4 minus x squared minus y squared. So z is equal to root 4 minus x squared minus y squared. And then for the xy plane, we're going to have y is equal to negative root 4 minus x squared, or to root 4 minus x squared, and y and x is equal to negative 2 to 2 of sine phi. Now phi was essentially the tangent in was hold on. It was the cosine inverse of z over the square root of x squared plus y squared plus z squared. So we're going to have, this is z over rho, so this is going to be it. The sine of this, so it's going to be or just r over rho. Or could have just used sine phi is equal to just r over rho. That would have been easier. Here, because then r is just square root of x squared plus y squared over the square root of x squared plus y squared plus z squared. dz dy dx. And then we have to subtract out the cylinder. So we're going to have the cylinder, which is defined as x squared plus y squared is equal to 1. For this z, we're actually going to have to find the intersection between the sphere and the cylinder. So x squared plus y squared plus z squared is equal to 4. And x squared plus y squared is equal to 1. So 1 plus z squared is equal to 4, z squared is equal to 3, z is equal to plus or minus root 3. So on the first part, we're going to have z is equal to negative root 3 to root 3. That's going to be the intersection. And then for the xy plane, we're just going to use y is equal to square root of 1 minus x squared, negative to the square root of 1 minus x squared, and x is equal to negative 1 to 1 of this whole thing. Yep, that's Cartesian. It is nasty. Alright, cylindrical coordinates. This one is not that bad to do. Because we get just square root of 4 minus... Because we get, where was it? Oh, that's it. Square root of negative square root of 4 minus r squared to square root of 4 minus r squared. R goes from 1 to 2. Theta goes from 0 to 2 pi. And then sine phi is just r over square root of r squared plus z squared. Times r dz dr d theta. As for d, cylindrical would be the best because we have a cylinder. Alright, and that's all of 5. Any questions? I am. Alright, let me just see. Can I see the answer for 4 one last time? Okay. So here was the answer for 4. It's essentially two separate integrals. The first one has from negative root y to root y. This describes the parabola itself. When it goes from the parabola y equals x squared to itself, and y equals to 0 to 1, and then the other integral is y equals 1 to 4. Or this one goes essentially from the line that was defined by y equals x plus 2 to the right side of the parabola. Y dy. And that's it for number 4. For the people who are lost, so we started off with cylindrical coordinates, and it's to describe R. Knowing that we have a cylinder or radius 1 that is outside of, our lower bound for that is going to be R is equal to 1. And then the sphere gave us x squared plus y squared plus z squared is equal to 4, which is just the equation for a sphere. And then x squared plus y squared is equal to r squared. So it's going to be r squared plus z squared equals to 4. We will solve that for z and put that as our bounds for z. R will go from 1 to 2. Oh, and because we have no restrictions on x and y, we'll have theta go from 0 to 2 pi. This is the easiest one to do. For spherical, we have one of the bounds be rho is equal to 2. This is from the sphere. And then we want to remove the cylinder, so we must start from essentially where the cylinder is, and keep going. So we have the cylinder defined as rho sine phi is equal to 1, from r is equal to 1. So therefore, rho is equal to cosecant of phi. That's going to be our lower bound. So our rho bounds are from cosecant phi to 2. For phi, we need to actually get rid of the part that's inside the cylinder. So we find the phi value that corresponds to that, and the one on the other side, but that's just pi minus whatever we find here. So here we find that this angle, which I called phi 1, is equal to tangent inverse of 1/2. So that and pi minus it will be our bounds for phi. And because no restriction on x, y, theta is from 0 to 2 pi. That is going to be for spherical. For a Cartesian, I just took the easy route and just did it with sphere minus cylinder in set notation, which is this. Basically just a sphere minus a cylinder. I was not going to make this into one set. As far as B goes, we're going to take the Cartesian. We're actually going to have to do the Cartesian thing. I did it again, sphere minus cylinder. So I just found the sphere bounds, which is from z is equal to plus and minus root 4 minus x squared minus y squared from the sphere equation. And then from the x and the y, we're going to take a projection onto the xy plane, which will give us a circle of radius 2. So again, y is equal to from negative root 4 minus x squared to root 4 minus x squared, and x equals negative 2 to 2. And for the cylinder of radius 1, and we're going to first find the z bounds, which are just going to be constants. So to do that, we'll find the intersection between x squared and y. X squared plus y squared equals to 1, which is the cylinder, and x squared plus y squared plus z squared equals to 4. Or what the heck is going on? So we're going to plug in x squared plus y squared equals to 1 into the sphere equation. So again, 1 plus z squared is equal to 4. Therefore, z squared equals to 3, and z is equal to plus or minus square root of 3. That's going to be our bounds. This is for this. And for the y, we're going to use the cylinder. Under equation we have here, x squared plus y squared equals to 1. So therefore, y is equal to negative square root of 1 minus x squared to square root of 1 minus x squared, with the x going from negative 1 to 1. Yeah, this question kind of sucks to do, but I did it anyway. Hey, the part that sucks the most is the fact that you have to parameterize sine phi into these other systems. It's just atrocious. Alright, does that help anyone who is lost right now? Because that's all the steps for 5b. 5c is actually going to be fairly simple because of these of the fact that we have a cylinder and a sphere here in cylindrical, so z is equal to plus or minus root 4 minus r squared. Whereas that's going to create the balance for that. R equals to 1 is from the cylinder, R equals to 2 is from the sphere. Yep, it's the sphere. Yep, it's the sphere radius 2 or the cylinder. And then theta goes from 0 to 2 pi because no restriction. Cylinder is probably the easier one just because of the region. Is there a best coordinate system? I don't actually know. They probably will all suck. Awesome. Okay, I'm moving. Is there any further questions? The silence is very unnerving. Okay, we're moving on to question 6. Someone wants it out, and honestly, I will also get it out of our sites. Okay, so question 6 has a vector field. F is equal to x, this vector x squared over 4 minus y squared over 2, comma x plus 2y. And it wants us to sketch at integer values such that, you know what, I'm gonna just use discrete math notation. It's better for this. X, y in integers such that -1 is less than or equal to x is less than or equal to 2, comma -1 is less than or equal to y is less than or equal to 2. And it asks us to make a table, so we will make a table for this. -1, 0, 1, and 2. -1, 0. This is going to be x, and this is going to be y. 1 and 2. Okay. So we're going to do the easiest ones first, aka when x is equal to 0 and when y is equal to 0. We're going to get -y squared over 2, comma 2y if x is equal to 0. So for x equals to 0 and y equals to 0, we're just going to get the 0 vector. If y is equal to -1, while x is equal to 0, we're going to get negative, that's going to be -1/2 I, -1/2, comma, -2. For 1, we're going to get something similar, x to +2. And for 2, we're going to get -2. Yep, -2. Comma 4. Like so. At y is equal to 0, we're going to get x squared over 4, comma x. So for this one, we're going to get 1/4, comma -1, 1/4, comma 1 again, and 1, comma 2. And that's all the easy ones taken care of. And the rest is just a plug and chug. So -1, -1, these squares are going to be helpful here. We can get 1/4 minus 1/2. That's going to be negative 1/4. We have -1 minus -2, so this is going to be -3. At 1, we're going to also get -1/4 because this is even. Except after this time, we're going to get that x is equal to 1, and y is equal to -1, so we're going to get 1 minus 2, -1. And here's -1/4 and +3, which leaves this one to be at y is equal to 1, we're going to get -1/4 again. And then x equals to -1 and y is equal to 1, we're going to get +1 for this one. For -1, 2, 2 when y is equal to 2, we're going to have that this is 2, and we're going to have 1/4 minus 2. 2, that is -7/4. Or -1 plus 4, that's going to be 3. 1 and 2, that's going to be also 1/4 minus 2, so we're going to get -7/4 here. And then 1 and 2 for this one is going to be 5. For 2 and 2, we're going to get 6 for the y coordinate, and then for the x coordinate, we're going to get 1/2 minus 2, or -3/2. 2 and 1, we're going to get, what is that? Of course I calculated this wrong. 2 squared.
Sorry to interrupt, but
yeah?
when there's a good time, could we revisit part 1b? Because I don't know, I have a question, and
Okay.
I'm not sure if it's...
Okay.
Okay, yeah.
Okay, I'll finish up this quick point, and then we can just go back to it really quickly. Alright, so 6, that's going to be 2 and 2, that's going to be 4/4 minus 4/2, that's 1 minus 2, that's going to be -1. Alright, 1b, what was your question?
Yeah, thanks. Wouldn't it mean if n dot, where is it?
F dot n?
It's like, yeah, n dot f, if it's normal, wouldn't it mean that n dot f equals 0?
N is not necessarily normal to f. If n is normal to a unit circle.
Okay, thank you.
No problem. Alright, back to the table. Let's see. 1 minus 1/2, we're going to get +1/2 here. Here, 2 and 1 is going to be 4. 2 and -1 is actually going to produce a 0. And then finally we have if x equals to 2, y is equal to -1. So we got 1 minus another 1/2. It's going to be a 1/2. Okay, finally done. And as for a sketch, I'm just going to do this. X, y, 0, we're going to get 0. -1/2, we're going to get -1/2. So at x equals to 0, we're going to get -1/2, -2, which is going to point down and to the left. It's going to point down more than up, so it's going to do this. This is going to point up and to the left like this, and then even more so like this. Then we're going to have negative at 1. We're going to have 1/4 of 1, which is going to be something like that. Then at 0. If x equals to 1, y is equal to 0. Then 1, we're going to have negative 1 4th 3. So that's going to go a little bit to the left. At 1, x equals to 1, y is equal to negative 1. We're going to go negative 1 4th negative 1 like this. And something like that. X equals to 2, y is equal to negative 1 will give us another 0. Will give us a 1/2 to the right. X equals to 2, y is equal to negative 1. One and 2. 2, 1/2 4. 1/2 4, and then 2 gives you negative 1 6. This y is equal to 2 will give me. Yep, this is just going to be a bunch of sketching. We're almost done here. Here it's just the y is equal to, it's just the x equals to negative 1 points. Negative 1, negative 1, negative 1 4th, negative 3. 3, positive 1 4th, negative 1. 1 and 1, we get back to negative 1 4th. With y is equal to, this should be negative. Negative 1 4th is going to be to the left and up. Yeah, 1 4th is going to be up, and it's going to be down to the right, and this is going to be up, down and to the right. It's going to be left and up, and then another left and up. Something like that! Not the best drawing, but it's going to be doable. Alright, number 7. For each vector field, determine whether it's conservative or not. If it is, find a potential function. Determine if vector field is conservative. If so, find potential function.
By conservative, they mean like a closed circle or something, right?
Conservative, I think, is just going to be using the definition. So it's just like the partial, using the partial. We're going to check the partial derivatives.
Can you explain that?
So for a two-dimensional vector field, where we have like a function of p of xy, comma q of xy. I should use capital F for this. F is conservative if q of partial of q with respect to x is equal to partial of p with respect to y.
Okay.
And then the other one has a bunch, and then for 3 case you have a bunch more. You have to check. I think p of x is p of z is equal to r of x, p of y is equal to q of x, and finally q of z is equal to r of y for the 3D case. So starting with A, we have f is equal to z over y, negative xz over y squared, x over z. Alright, let's go ahead and just start with q of x is equal to p of y. So q of x is going to be negative z over y squared. And p of y is Also negative z over y squared. That seems promising. P of z is going to be 1 over y. Wait, and this is where I can die. This is where I can actually die. The x over z. P of z is equal to r of x. Also, this is p, q, r, if that wasn't clear. R of x is 1 over z. Not conservative. Cosine of x, g is cosine of xy, cosine of xy. So q of x is negative x, negative y, sine of xy, and p with respect to y is negative x sine of xy. Not conservative. C. This is going to be a long one. Plus 1, comma, x squared z plus 2yz squared plus 2 to x squared y plus 2y squared z plus x plus 2z plus 3. Okay, q of x is equal to, this is p, this is q, and this is r. We're going to have 2xz, and that's it. P with respect to y is also 2xz. So far, so good. P with respect to z, 2xy plus 1. R with respect to x, 2xy plus 1. And the rest is gone. Okay, one more left. Q with respect to z. We have x squared plus 4yz. And r with respect to y. X squared plus 4yz. R is conservative. And now we have to find the potential function. Alright. We're going to just integrate. To do this, we're just going to integrate each one of these with respect to either x if it's going to be p, y if it's q, or z if it's r. I'm going to take x on the first one because it seems easy. So, this one we're going to have x squared yz plus xz plus x plus some potential function of y and z. We're not going to be adding a plus c because the plus c can be included into our g of yz. Now we're going to take the partial of r with respect to y, where r is going to be also defined as this thing. So this is going to be x squared z plus g prime of yz, z actually g of, or actually g with respect to y, which is equal to x squared z plus 2yz squared plus 2. And so our g of y is going to be 2yz squared plus z. So g of yz is going to be equal to, we're going to integrate this with respect to y, which is going to become y squared z squared plus 2y plus another function of z this time. Partial of r with respect to z.
What are you adding there?
Huh?
What are you adding there?
On where?
The g of yz equals the integral of 2yz squared plus 2d. Right above the partial r partial z.
Oh, the g of yz?
Yeah.
That's because
What
when
are
we
you adding there?
that's because when we integrate 2x this expression with respect to x, if we suppose we took a derivative of the expression we got back, if there was another function of y or z, it would become 0 and get annihilated. So when we try to find the potential function, we have to account for this with another function. This is also why we don't have the plus c, because that could also be inside the function itself. And then we need to find whatever this g of yz is, such that all the other partials line up, because we know they have to.
So what is it that you are adding?
Whatever expression we get over here. And then we have to find h of z and do the same thing. Plus xz plus y squared z squared plus 2y plus h of z. And now I take a partial of this whole thing with respect to z. We get x squared y plus x plus 2y squared z plus h prime of z, which is equal to x squared y plus x plus 2y squared z plus 2z plus 3. So h prime of z is equal to 2z plus 3. And now we're going to have to find h of z by integrating this with respect to z. Z squared plus 3z. And now it's a plus c, because we actually reached the end. So, our potential function is x squared yz plus xz plus y squared z squared plus 2y plus z squared plus 3z plus a c, where c is an actual constant. And that's question 7. Any questions?
So you're just the potential function is the integral of each partial derivative.
The potential function is the function such that when we take the partial of that with respect to x, we get p. With respect to y, we get q. With respect to z, we get r.
And you add all those up?
Yeah, we add all of them up over here. Essentially, we start with we start finding out the potential function of just considering x. Then we account for the fact that a function of y and z could have gotten destroyed by taking the derivative back. So we account for that. We try to find what that function is. And then we do this twice because we have this g of yz that could have also where a function of only z could have also gotten destroyed from taking the partial with respect to y. So we account for that.
So for your potential function, if you do take the derivative of the potential function with respect to x, y, or z, you would get that vector field you have right now.
Yeah, if you were to essentially have the differential operator on this function, so partial with respect to x.
Okay.
X is basically the differential operator times this function, basically.
And what happens when 1 equals 0?
What? And 1 equals 0?
not quite sure, but I remember in the homework problems, at times you would find that when you were either trying to cancel them out, somehow they would equal 0.
Yeah.
But I'm not quite sure like what went on there.
Like, when do you get 1 equals 0? Like, what do you mean 1 equals to 0 here?
Not 1 equals 0, but you just
when one of the potential functions equals 0.
Yeah, probably.
I mean, that just means it would just be completely, it would just exist. You could just plug in 0 back into this equation and be completely fine. It wouldn't really do anything if you find no extra function here.
And if q equaled 0, does that mean r is like guaranteed to be 0 as well, or that it could still be something else?
If q is 0, well, I'm not actually too sure. I think you could have it actually where it's just x and z, and it would be conservative. Yeah, you could have it as x and z and just be conservative. It'd basically be the 2D case, but with p and r instead of p and q. So you could have something else. Because then q of x and q of z would be 0, p of y and r of y would have to be 0. So therefore, you would actually just be resulting into the 2D case, really.
Okay, thank you.
No problem. Anyone else have any questions? All right. I guess I'm moving on then. Number 8. Okay, this one's a little bit of a weird question here. Because it gives us a graph for this vector field. So consider the vector field f is equal to pq, shown below. I'm actually going to just draw this in. In is essentially just going to be like this. More straight the further I go. Something like this. Something like that. A sketch two different non-intersecting curves C minus and C plus that have the same initial and final point such that the integral of C minus of f dr is less than 0 and C plus of f dr is bigger than 0. Okay. So this is clearly a line integral. We're going to have so over 0 it means it will tend to go. I think you need to. I think for this one you are going to need to use interpretation for the line integral. In that case, we have give me just 1 second. Okay. So basically, we're going along the feet. So basically, I think what this means is going to be that we essentially go along on the direction of the flow here. So here, this flow is clearly going clockwise for the most part. So I can have C plus be this curve over here. If you're seeing it, I'm going to use a different color. C plus in blue. And then C minus be red here. Where C plus will go in the direction that I have. So it'll go from this initial point to this final point here. So this is initial, final. No, this one goes in this way, and then this one has to go against the direction of the flow, so it'll also go that way. So it'll also go like that, counterclockwise. Like so. This is essentially just supposed to be like a unit circle or something, so just 1, -1 like that. Just make that a unit circle. Well, the reason why is because of B. Yeah, because this encloses a region. This question asks is this integral positive, negative, or 0? So in this case, because of how we defined it, I think it should be. I think it should. Yeah, it's going to be 0 if I'm not mistaken, because we can actually find 2 points on every single point such that they'll be negatives of each other. So this point and this point, which are effectively like pi over 4 and 5 pi over 4 are going to be negatives. These two are going to be negative of each other, and so on. So equals to 0. because this is at a certain point along this curve, I can find another point such that those two have the negative are negative of each other. Same goes with any point inside the region. Inside the region, if I reflect it across this y is equal to x or y. Yeah, y is equal to x, I'll find a negative.
But wouldn't a number minus negative that number be like 2 of that numbers? Wouldn't you be adding?
Yeah, you'd be adding. I think you'd be adding. It's anything inside the region. Now, so this whole vector is effectively just going to give me a one value, and then it's going to give me negative of that on the other. So and when you're going to add those two up because the integral is a sum. So you're adding a bunch of things that'll cancel out. Because the integral is basically another form of summation.
Yeah, okay.
So for all points x, y in the region D, there exists a point. This is reflected across x equals to y, I think. Yeah, x equals to y. It'll reflect across that. Such that q of x minus p of y evaluated at xy is equal to negative of q of x minus p of y evaluated at yx. Here is a little bit of a more visual demonstration of it. It's a little bit easier to see with the actual diagram they give you. But if you essentially look at it, it's going to go for any single point on that, any point that's even on the diagram itself. If I reflect it across onto y, cross y equals to x, you will just get the negative of whatever that's on. At least you should, yep. Yep, that's gonna reflect across y equals to x on the other side, and that's gonna be a negative. That's negative. That's gonna be a negatives. It's gonna be perfectly negative. If that's y equals to negative x. Next, but that reflects across this way, so yeah, you actually just get a reflection across y. Every single reflection will give you a negative, yeah. So this is equal to 0. So now it says to choose the function. C tells us to choose the function that corresponds to this vector field. So it gives us a few different options. But since we know damn it. Okay. Y minus x. And then y minus x, y plus x. And the fifth one is going to be x plus y, x plus y. So we want q of x is equal to p of y because we just decided that this was, from part B, we know that this integral is 0. from the fact that for any single point I can find a negative of that. I can just find a negative of that inside the circle. Oh, and you can also show that everything will be that for any point, if I do y squared plus x squared, you'll also get the same thing. So there will always be a point inside the circle. So we're good for that one. And also, if you notice on the graph, if x is equal to y, then q will be 0. Because all of those on there only move in the x direction. Another thing we can observe is that if x is equal to y and x is bigger than 0, well, p is bigger than 0. And if x is equal to y and x is less than 0, p is less than 0. So with all that information, first q of x equals to p of y. For the second one here. So for the first one, actually, we're going to get a 1 here and a -1. So this one's out. For the second one, we're going to get q of x is -1 and p of y is +1. I'm actually going to do it outside of it. So yep, q of x is 1, p of y is -1. Q of x is -1, p of y is 1. Q of x is -1. One, and then p of y ends up being 1. P of y is 1, q of x is -1. So those three are all out. Here, they're both equal to 1, and here they're both equal to 1. They're both equal to 1. So these are the only two in the running. Hold on. Need to check that. One other one should have been in. Then q of x is equal to -1. Yep. And then q of x here is going to be equal to q of x is equal to -1, and then p of y is equal to 1. Yep. Q of x is equal to -1. P of y, that's going to be positive. So p of y is equal to 1. X plus y, yep. That's going to be 1. X minus y is going to be x minus y. So y, q of x is equal to 1. And, oh no, this should be in. This should be still in. Yep. Q of x is equal to 1. P of y is equal to 1. 1. Yep, that's still in. Okay. If x is equal to y, q is equal to 0, this eliminates the fifth one. And if x is equal to y, which we're going to get, and we want q is equal to 0. 0, that is not a good one. Well, that is good. And also, then we also have if x is equal to negative y, or y is equal to negative x, we get p is equal to 0. Right, so we should get it in this one then. So then it should be. I'm gonna get rid of this for a second and see if that fixes anything. Still eliminates the fifth one, as you can't get that. Get that. And the correct one should be... It'd be, what is that? It's gonna be x is bigger than 0, p is bigger than 0. If x is bigger than 0, p is bigger than 0, and q is equal to 0. Equal to 0 means you have these two, one of these two. So it should be this one then. It should be this one. Based on all this information. Which makes sense. If x is set to 0, we're going to get y and y. Y, yep, that is the right one. So let me just see what the math is going to be. I see what's happening. It's because the orientation's flipped. It's because this goes into single orientation, which means one of them's going to be flipped. Orientation. So all of these are actually the same thing. Let me just see. Hold on. Let me just see where the logic is really quickly, because this should be the right one. One based on everything given. Q with respect to x is going to be -1, and p with respect to y is 1. 1. So this means there's something wrong in b. Give me 1 second. I'm just trying to figure out what happened, what I did wrong in the problem. When this is going to be the right function, though. Yep, if x is equal to -y, p is equal to 0. Yep, this is indeed the right one. This is the only function that'll do, even just the first and fourth ones. So this means that A and C are right, B is not. And if that's the case, then Y is a... Okay, if I orient this... because it's oriented yeah, it's oriented clockwise, and then the circle will be oriented counterclockwise, so we got a negative, so we get a negative there. Okay, and that fixes the issue. Yeah, that fixes the... Awesome, this is gonna be it. Clockwise. Is oriented counterclockwise. I like this one better. Okay, so it is negative. Yeah, it turns out because these are now oriented in a single way, so now you have to get that. Awesome, that's it. That's about it for 8 then. Just had to fix that one up, and we're good. Is there any questions? Yeah, this is the right one. This should be the right one based on the information given. So So x is equal to y, q is equal to 0, so y minus x, or x minus y is q. Q, yeah, and then x plus y, or negative x minus y. Y, so x plus y has to be p, so this is going to be the right one. One, and therefore it's negative because of the vector field spinning clockwise instead. Whereas we're going to move counterclockwise. Okay, moving on to 9 then. Okay. Okay. So part A of the previous question is not possible in. So it says why 8A is not possible in the case where f is equal to y comma x. Okay. Okay. 8A is essentially just sketching two different non-intersecting curves that have the same initial and final point, such that one of them is less than 0 and the other one's bigger than 0. Explain why that's not possible. So, it's going to be maybe because of whichever one. Oh, let me see the chat. Chat's updating. Yep, just a few more problems left. We're on problem of 9 right now. Oh, so explain why 8A is not possible with fyx.
I think it's because you wouldn't get the same 2 points. It's not. Is it rotation? Yeah, it's not rotational.
Like irrotational? Oh yeah, that's
Sure.
it. Yeah, irrotational, because it's irrotational and you're not going to get a single curve. You're not going to get a curve that does it. Thank you. Yep, actually. Yep, because q of x is equal to p of y. Y is equal to 1. When f is conservative, thus curl f is 0. Thus f is irrotational. So we cannot. So therefore, we're going to have for any curve C of FDR is either only positive or only negative. And we cannot find one, therefore you cannot find one. Because all the curves have the same sign. Okay, I think I like that one. Okay. Yeah. Number 10. So it says that the density of dust collected by a single passage of a vacuum cleaner is given by d of xy is equal to 5 plus x squared y. I think this is in grams per meter or something. How much dust would be collected by a vacuum cleaner traveling counterclockwise along the upper semicircle of radius 2 centered at the origin? So the radius thing will be this. This is radius 2, and this is the upper half of this. So the easiest way I'm going to do this is to parameterize this equation. So I'm going to say x is equal to 2 cosine theta and y is equal to 2 sine theta, because that's how we parameterize circles. And then because we're only dealing with a half circle, I'm only going to deal with between 0 and pi. So d of theta will now become 5 plus 8 cosine squared theta sine theta. And now I can just integrate this. That's sine squared. Cosine squared theta sine theta d theta. I think we have to do times magnitude of the derivative. Yep, I have to do magnitude of the derivative. R of theta is equal to this. R prime of theta is equal to negative 2 sine theta to cosine theta. And then the magnitude of this is just going to be 4 sine squared theta, 4 cosine squared theta is actually just 2. So I just put a 2 in front. I'm going to split this up into two different integrals. So 10 d theta plus 16 times the integral d theta. This is going to be u is equal to cosine theta, du is equal to negative sine theta, theta d theta. The first one just evaluates to 10 pi. Now when you get 0, you get 1 to negative 1 minus 16 times u squared du. And I'm going to flip the bounds using the negative. Which is equal to 10 pi plus 16 times u cubed over 3, evaluated from negative 1 to 1, plus 16 times 1/3 minus negative 1/3. This is 2/3, so 32 over 3 plus 10 pi. Number 11. Oh, any questions? I ask that every time. We're almost through. Okay, I'm moving on. If anyone has a question, please speak up. 11. Compute the curl and divergence of the following fields. At the given point. All right. 11a g is equal to x plus y, comma, y minus x at the point 4, 4. And then so it gives us also 5 separate questions to do. So first we have the divergence of g is equal to partial of the first one with respect to x plus the partial of the second one with respect to y. Curl of g, which I think is just going to be qx minus pyk, because this is a 2D. This pyk, which is negative 2k. This is going to be regardless of any single point. So that's it.
Can you explain how you did the divergence one?
Okay, the divergence is just the partial of this of p with respect to x, because it's the first one, and then plus q with respect to y. Because it's essentially just del dot g, which is partial with respect to x, comma, partial with respect to y, dotted with x plus y, comma, y minus x. You see it now?
Yeah, but the partial with respect to x would be one and the same for partial of y.
Yeah.
If you dot that with x plus y and y minus x, wouldn't it be x plus y plus y minus x?
The thing is, the partial is getting first and then added. The partial is getting added is going first, and then we're adding it. So you start with the partial of x plus y, and then partial of y minus x. The partial of x with respect to x of x plus y is 1. The partial of y minus x with respect to y is also 1. And we just add those two together.
Okay.
All right. Would there be a tendency to rotate at the point? Yes.
All right. What are would it why do we have that 4, 4 there?
4, 4 there is actually a point given to us, but it's completely useless because we don't actually have to plug anything in.
Okay.
Yeah, it says to evaluate at the point, so I keep all the information, but we really don't even need it. Tendency to rotate at the point. What would be the speed and direction of any rotation? So I guess that's just magnitude of the curl vector. So rotated direction minus k and speed 2. And not incompressible and not irrotational. B. F is equal to y x at 2, 8. This is going to be another one where we might actually not need the point at all. Yep. Div f, first we're going to have f partial of the first one with respect to x, which is 0, and then the partial of x with respect to y, that's also 0, so we get 0. Curl f is going to be equal to q of y minus q of x minus p of y. So it's going to be q of x is going to be equal to 1, and then p of y is also equal to 1, so we get 0. So incompressible, irrotational, speed 0, direction nothing, because we don't even need a direction, there's no speed even.
How do I know when one is incompressible or irrotational?
Incompressible means div f is equal to 0, and irrotational means curl f is equal to the 0 vector. It should be the 0 vector because there's a k here. Alright, C. R is equal to x squared, comma, negative y squared, comma, 2yz minus 2xz at the point 3, 1, 2. We're going to have then afterwards, okay, the div of R is going to be equal to partial of the first one with respect to x, 2x, minus 2y, because this is negative 2y, plus 2y minus 2x, of course. 0. Curl of R. Now we're actually going to have to use the cross product for once. Partial x, partial y, partial z. So, starting off, we have 2z minus negative y squared minus negative 2z minus x squared j plus 0 minus 0. So 2z plus y squared I plus 2z plus x squared j. And now we get to use the point. To 2 times 2 plus 1 squared I plus 2 times 2 plus 3 squared j to 5i plus 13.
Where did the y squared come from in the I component?
Oh, that should be a 0. That should be a 0.
Yeah.
That should be a 0. And the other one should also be 0, so this should be entirely just 4i plus 4j. Plus 0j.
Isn't that supposed to be negative? Or did you account for that?
Oh, yeah, that should be, oh yeah, I did account for that one. I did account for that. Because if you're doing this one, you'll get a negative 2z, so that gets cancelled out. So it's accounted for. And then the other one is 0. 2zi plus 2zj. So we just get 4i plus 4j. That's all we get. Alright, this is incompressible. Tendency to rotate. Speed is just the magnitude of this. So it's going to be 4 root 2 over 2, I think it is. No, it's going to be square root of 4 squared plus 4 squared, which is root 32. Which is, yeah, 4 root 2. 4 times 4 root 2. And direction is equal to 1 over root 2 times I plus j.
Where did the direction come from?
It came from the curl. It's essentially, if you make the curl a unit vector, that's the direction of the rotation.
Okay.
Awesome. Any more questions? Okay. 2 more left. 2 more left to go. 12. Parameterize and find the unit normal vector to the following surfaces. The paraboloid z is equal to 4 minus x squared minus y squared, oriented upward. Okay, so first we're going to do the parameterization. So whenever we see an x squared and y squared, we're probably going to deal with a cosine and sine for those. So when we have we're going to have x just equal to r cosine theta, and y is equal to r sine theta. And in z, if we plug in r cosine theta and r sine theta into the original, we get 4 minus r squared. Here's the entire math. Math minus r sine theta squared. This is equal to 4 minus r squared times cosine squared theta plus sine squared theta, which is just 4 minus r squared. So that's going to be our parameterization. And for the unit normal, what we're going to do is we're going to put everything except for a constant to one side. And then our normal is just going to be the gradient of this function. We're just going to name it f of x, y, z. over its magnitude. So we're going to get 2x comma 2y comma 1 over the square root of 4x squared plus 4y squared plus 1. And that's it. That's it for A at least. Does anyone have a question? Hello?
So what exactly did you do here?
Okay, so basically the idea for the normal for the first part is the parameterization. So when we see here to parameterize this surface, what I can do is I see an x squared and a y squared, so I can have like z equals to 4 minus in parentheses x squared plus y squared. If I make this an r squared, if I just make this r squared, I could just have z equals 4 minus r squared, and then just essentially borrow from cylindrical or polar to get the other parameterizations.
Okay.
That's the parameterization. For the unit normal, what you can do is if you put everything to one side except for a constant, what you have here is essentially just a level curve of a function with such that this function is just all these variables here. This isn't just a level curve now. So the normal to the level curve is now going to be a gradient. And now with the magnitude of that, we just divide out so it's a unit normal. And that is it for that one. B. Square root over 9 is equal to 1. Oriented outward. So we're first going to look at this portion. This almost looks like x squared plus y squared plus z squared equals to 1. Borrow from spherical with rows set to 1. Z squared over 9. So z over 3 is equal to this should be cosine phi. And that's our parameterization. Essentially, the idea is we're just going to borrow everything from spherical. With rho is equal to 1, so we only have 2 variables instead of 3. And then to account for the z squared over 9, I'm just going to set z over 3 to be cosine of phi, so z is 3 cosine of phi.
Since you're converting some parts to spherical, will you not need to do the rho squared sine phi at the end?
This is not an integral. This is just a parameterization.
Okay.
So there's no rho squared sine phi for this one. We're just borrowing a lot of stuff from spherical because this almost is a sphere, except for the fact it's squashed. Or actually not squashed, stretched. Because it's stretched out. And the unit normal is just going to be, again, we have effectively just another level curve. So x squared plus y squared plus z squared over 9 is equal to 1. So we're going to just do the unit normal, gradient over magnitude of gradient is equal to 2x, 2y, 2 ninths z over square root of 4x squared plus 4y squared plus 4 over 81 z squared. And this is the outward one because these are all positive. One because when x, y, and z are positive, this is also positive. When x, y, and z are negative, they're going to go negative in their respective directions. Yep, this is outward. And that bottom part is always positive. That's it for number 12. Anyone have any questions?
No.
Uh-huh.
No. No questions.
No questions? Okay, I'm moving on to 13 then. This is the last of the exam review. Nice. Let S denote the surface. Z is equal to square root of x squared plus y squared. For 1 is less than or equal to z is less than or equal to 4. Oriented up. Just going to do oriented up like that. So first A says to give 2 parameterizations for S. Alright, time to start borrowing stuff. First, I'm going to just try and borrow from cylindrical. Using x squared plus y squared is equal to r squared, I could just have z is equal to, let's see, x squared plus y squared is equal to r squared, so therefore z is equal to square root of r squared, which is going to be just r. So therefore our parameterization can just be, let's see, I'm just going to use r1. R1 of r theta is just going to be equal to r cosine theta, r sine theta, and r. Let me see, can I borrow from spherical or not? Sometimes you can, sometimes you can't. Because this is just a phi equals pi over 4 situation. Z, oh yeah, I can just do this. Z is equal to square root of x squared plus y squared. Squared, this becomes rho sine phi is equal to rho cosine phi, which becomes sine phi is equal to cosine phi, which becomes phi equals to pi over 4. So now I can just set our second parameterization with just rho and theta now.
Did the cosine theta and sine theta components, were they squared and then equal to 1?
Yeah, cosine squared plus sine squared will give you 1.
And that's what you did there?
For which one?
When you try to switch the x and y to spherical coordinates.
Okay, when I try to switch them, you actually get x squared plus y squared, and then it is equal to r squared is equal to rho sine phi squared again. Which also does the... This is the part we're actually using from spherical. And then we're ignoring all the negative solutions here, because we only need the positives. So phi is equal to pi over 4. Now all I have to do is just plug this into all the parameterizations, so I only have 2 variables instead of 3. So rho sine of pi over 4 cosine theta. Y is equal to rho sine of pi over 4 sine theta. And z is equal to rho cosine of pi over 4. Or we're going to get root 2 over 2 rho cosine theta, root 2 over 2 rho sine theta, and root 2 over 2 rho. Which I just realized is literally the exact same thing as the other one, except instead of rho, you have root 2 over 2 rho. I mean, instead of r, you have root 2 over 2 rho. But hey, it's another parameterization, so it works. Alright, there's our 2 parameterizations. Awesome. B and C left. Evaluate the integral f dot ds, where f is equal to negative x over root squared plus y squared, 0 x y. Alright, so first we're going to have to... So I'm going to take the parameterization from the other surface, from cylindrical. So r1 of r theta is equal to r cosine theta, r sine theta, and r. Now because z is just equal to r, we're just going to get r goes between 1 and 4. And then because x and y have no restriction, they could be negative or positive, we'll have theta go from 0 to 2 pi. Because there's no restriction on theta. So this integral s f dot ds. Okay, we're going to have to find some. Okay, this is where a bunch of new stuff actually comes in. These are the right bounds. But now what I have to do for this one is I have to find R1. I'm going to make this... You know, I'm going to just use rho for this. I'm just going to use rho because I'm running out of letters. Rho with respect to r cross rho with respect to theta. I have to find this vector. So this is your I, J, K, and then each component with respect to r. Cosine theta, sine theta, 1. That one's a 0, and this is going to be negative r sine theta, r cosine theta, and then 0. we're going to get nothing minus r cosine theta I minus 0 r sine theta j plus r cosine squared plus r sine squared. So something like this. Squared k. This is now what we're going to have to dot this with. Dot f with.
Why did you use the cross product there?
Okay, it's inside your form. It's in the formula sheet, but essentially, when you have a surface integral, your ds is going to be just technically your ru cross rv, but I renamed everything, so it's just this with respect to r cross rho with respect to theta, like this. When you have a vector function like that, it's in your formula sheet.
Okay. Isn't there like an arc something as well? When you're trying to find the surface area or something, aren't you supposed to find the arc?
We're not doing C yet.
Okay, that's something else then.
Yeah, that's probably either going to be something else, or it's just going to be like, we're going to set it just to 1, so we're just going to have this row, the ds, and that's it.
Okay, thank you.
Yeah, this one we're going to dot for now. For now, we're just going to dot it with that. And now we have to now parameterize this with r and theta. This is where the r cosine thing comes in handy, because I have now x is equal to r cosine theta. Square root of x squared plus y squared is just r, so we actually just get negative cosine theta. How nice. 0, and then xy is just r squared cosine theta sine theta. Dotted with negative r cosine theta, negative r sine theta. R squared again. dr d theta. There is no r this time around. R is equal to 1 to 4. This is going to be r cosine squared theta. The y is gone, plus r to the 4th cosine theta sine theta. dr d theta. Now we just calculate this and we'll be done. Theta is equal to 0 to 2 pi of r squared over 2 from 1 to 4 cosine squared theta plus r to the 5th over 5 cosine theta sine theta dr d theta. Okay, I'm gonna have to calculate. I'm gonna have to actually calculate 4 to the 5th on this one. Okay, 16 over 2 minus 1 over 2. This is going to be 15 over 2. And then we get 1023 over 5 cosine theta sine theta. This should be a d theta.
Why is that 15 and not 16?
Because r squared over 2 evaluated from 1 to 4 is going to be 16 over 2 minus 1 over 2.
Oh.
Yep, there was an extra 1 there. Alright, and now I'm just going to have to rewrite this. So we get 15 over 4 times 1 plus cosine of 2 theta plus 1023 over 10 sine of 2 theta. 15 over 4 theta minus half, no, plus half sine. 0 to 2 pi plus 1023 over 10 negative half cosine of 2 theta from 0 to 2 pi. Which negative 1/2 cosine from 0 to 2 pi will just be negative 1/2 times cosine of 4 pi is just going to be 1 minus cosine of 0, which is also 1. And then sine will have a similar thing, so we're just going to have 15 over 4 times 2 pi minus nothing. Or 15 pi over 2. Here is the actual whole thing up to the side. Actually, there should be, no, these should be pluses. Okay. And that's B. Now we calculate the surface area.
Carlos.
Which is just going to be this. So now we just calculate this. This, except now we need the magnet, except now we're actually using a scalar function instead of a vector one, so we need to use a different ds here. This ds is not the same as the other ds. It's going to be the magnitude of the other ds we calculated. So we get r squared cosine squared theta, no, not cosine 2, plus r squared sine squared theta, plus r to the 4th. This is the square root of r squared plus r to the 4th. And it looks like I'm going to have to factor out an r squared from that. So 1 plus r squared from that. And that's what I'm going to put in inside there. Theta is equal to 0 to 2 pi. I'm going to move this down. Of r times root 1 plus r squared dr d theta. Does this one have it? Hold on. Does this one have an r? I don't think so, because it's just a magnet. Because I'm just using a scalar function. This is as if we have... No, this one's a dA. Nope, this one's dA, so there is an r. Oh, I'm going to have to trick something, don't I? Yep. Awesome, I'm going to be... Awesome, this is going to suck. Yeah, it's not like it would have been any better. Hold on, would it have been any better with the other formula? There's another formula that also calculates the surface area. Area for this kind of stuff. That would have also worked. So dz dx, that would have just been x over this. Give me 1 second. This should be the left. I'm going to see if this is actually intended or was a mistake made. It's a different formula. Squared plus a 1 here. Here, this gives you x squared plus y squared over x squared plus y squared. Yeah, you get root 2 from this. Hmm. You get root 2, which would become root 2 RD theta. Because I know there's also another one that's like dz dx plus dz dy, y plus 1 dA. There's also this formula for it. I'm trying to see if these are the same thing. Hold on. Hold on. Is this even an R squared? Yeah, this is not even an R. Nope, that's an R. That's just a regular R. Oh, that's a regular R. That's why. That's why we're having. That's why it was weird. Fix this. Damn it. R to the 4th over 4. Yeah, that's why this is. This will change the answer. This will not change. Actually, will not change the answer because only the other one had to have an issue. And then it'll be much easier. This is 255 over 4. Yep, and that's gonna fix the issue actually. This is 255 over 8, and it will change the answer though. 255 over 8. And that still goes to 0, so that's gone. R squared, this is R root 2. Oh, there, okay, there we go, there's the issue. That was the issue, that was straight up the wrong one. Yep, they are the same formula. You're gonna get rid of that. This is gonna be R root 2, the 2, and now I'm gonna calculate this. Root 2 times R squared over 2, evaluated from 1 to 4. And then this is going to be root 2 times 16 over 2 minus 1 over 2, 15 over 2. And then this is a constant, so we're going to get 15 over 2 times root 2 times theta from 0 to 2 pi, which is equal to 15 pi root 2. And that's it. That's the entire exam review. Three and a half hours in. What was that for?
My brain is fried.
Oh god. And it's required there was like a few extra concepts in here. Here as well. That's like, yeah, that's gonna be heck. Okay, do you want me to send all of this over?
Yeah.
Okay, this is gonna be, oh god, this is gonna be a hell of a lot.
Is it possible to like shorten or split parts?
Yeah, I'm gonna split this up by a lot. Don't worry, I can do it, it'll just take a while. Alright, this is the first picture of who knows how many. No. Let's see if I can take 6 through 8. Oh god, and this is not going to get any zoomed in any further. Okay, I'm going to see if I can fit 9 through 13 in this. This is why I said it was. This is why I said it was watching me suffer. This should be 1 plus. This should be 1 plus 1. 1 is not squared there. Alright, and time for light mode. Oh my god. Oh my god. Yep, Discord is. I think Discord is unresponsive. Oh, that sucks. That means I'm gonna have to leave and rejoin the call again. Yep,
Oh, he left.
I'm back. I just had to. Discord became unresponsive. Oh my god, don't tell me this unresponsive again. Oh, never mind.
Is that a server with you as a profile picture?
Huh?
Is that a server with you as a profile picture?
Yes.
The top one?
Yes, that is indeed me. I put that like a long time ago. Oh, so that's like not even indicative of my face now. Why can't I press the button? Oh my god, please don't tell me I have to leave. I have to actually just straight up make freeform gone so I can just actually get the picture in. Well, I'm doing this again. Well, time to leave and rejoin again. And we're back. Alright, let's hope this works. Oh my god. I hate when this happens.
Did you end up finishing that song you were planning on doing?
The instrumental was done like a long time ago, and I haven't received anything back since. Yep, once I get these, I could just show that one once we're done with this. I could just show what I have for that. Awesome. It has been sent over. Exam 3 review problems have been sent over now. Awesome. Are we gonna do anything else math related, or just call off the recording here?
I don't know about everyone else, but my brain is fried. So I think
Okay.
maybe
brain fry.
leave math for either later, tomorrow, or some other day.
Yeah, sure. Yeah, sure. I'm gonna call off the recording and then right here then.